Hi everyone. In the last session, we completed the meshing and imported into the Fluent environment. This is the map meshing that we finished last time and checked the mesh also. So in this session, we will continue to do the simulation, set up the simulation of the advanced model. All the conditions that are required for the simulation are already stated in the guidebook. We will follow the same method, and the first thing we will define our is the physics that we will define is completely stated and solved in the Excel files accompanying the guidebook. So most of the things that uh, almost all the things uh, are, are written in the guidebook. So all the variables that we need to set up are written in the guidebook, and the values are calculated in the Excel files. So we can see that everything is calculated. We will directly just simply input all the calculated values in this session. So you can follow the guidebook in and the video sessions to set up your own model also. And in this session we will complete till the point where we get the first analysis, starting with this. So and then later on we will continue with the parametric analysis afterwards, but in this session we will only solve for the first analysis, that's all. So continuing with this session, to start with this session we first need to start the SOFC module. We already checked the extents of this mesh, so we'll skip that part and we'll directly start the SOFC module. But before going to that, we need to check if whether our electrolyte surface is at the correct position. So we'll first directly select all of these fluid conditions and display them. By doing so, we help afterwards when we do the post processing. It helps to give these solution for these to be present in the display menu. So if you go to display right now, there are no solid zones or any zones available right now. So if we display them, now you see we get all these fluid and solid, all these within the display menu also. So it helps a lot when we move on to the when we do the post processing, and especially the control plots for temperatures and partial pressures of the species. Then it will be very helpful to have the fluid zone and the solid zone within the display menu. The next important thing is to get the wall electrolyte anode and wall electrolyte shadow. We need to check that. So I will go to the boundary conditions and check the wall boundary condition and go directly to the wall electrolyte anode and double click it and check whether if it is the adjacent cell zone is AFL or CFL, because it can be CFL also. So if it is CFL, we will rename it to cathode. And in this, now the adjacent the shadow face zone is anode shadow, and that should be belong to the cathode side. So we'll close this and wall electrolyte anode shadow. We'll rename it to wall electrolyte cathode. Wall electrolyte cathode and apply. And to get it in the display menu, so we should also display in mesh. So okay, so now in the display menu, if you go, we will have all the options for the fluid zones, inlet, outlet, solid zones, and wall electrolyte anode and wall electrolyte cathode. And we'll just right for now just display everything. And this is the original menu, so we included in the display menu all the cell zones. And now we'll start with the definition of our model. For starting that, we will start it with the SOFC module. So we'll go directly into the energy equation. We need to turn on the energy equation. This will be laminar. Species, we need to species transport and volumetric reactions are present. And finally, we need to start the SOFC model. So for starting the SOFC model, we'll define it. For so this will start the SOFC module with unresolved electrolyte. Now we go directly into the SOFC module and enable. Here we should now, because this is the advanced model. Earlier we did not use the Knudsen diffusion, but now we will use the Knudsen diffusion also, and the coefficients will be calculated with it. The current under relaxation factor for the first time we will keep it at 0.2, and then the corresponding will take it at 0.01. The electrolyte we have taken from the reference 1.05 exponent minus 5, and the resistivity we have calculated it. You can see these values, the calculation values from the Excel files. So I'll show you the Excel file for calculating the conductivity. This was calculated using the equation given by the within the in the guidebook. It's already given and given also in the Ansys Fluent guidebook. Now apply. And for the electrochemistry, now the electrochemistry, the ion exchange densities are calculated for the references also, and the values used are from the PhD dissertation of Professor Y.D. Lee, and the values are calculated as which we will use in the simulation at the anode side and 0.46 at the cathode side. And the reference values, we take the reference values of 1 and the exponents are 1 1, and for O2 is 0.25. This the exponents actually belong to the equations that we use for the ion exchange densities, and the Butler-Volmer transfer coefficients, you take them as zero 0.5. They can be different also according to the model that we use. It's not necessary to be 0.5, but the model that we are using following the PhD dissertation of Professor Y.D. Lee, so here we use 0.5. Now we'll start defining the porous zones. For the porous zones, first we need the anode electrolyte, wall electrolyte, and wall electrolyte cathode, electrolyte, tortuosity zones, and so we have the AFL, ASL, CFL. These are all the zones which should have tortuosity, that are the porous zones. So all the porous zones should have this value. So we are just following the values that are referenced. Sorry, CFL is 5, ASL is 1, CCCL is 3.5, and for the mesh inverter and mesh cathode we have the minimum tortuosity. And now the nuts and diffusions. For the nuts and diffusion, we need to give the pore sizes. They are also given in the guidebook, how we have estimated the pore sizes for all these layers. So for the AFL, it's 3 exponent minus 7. For the ASL, it is 5 exponent minus 6. For CFL, it is 5 exponent minus 7, and CCCL, it's 7 exponent minus 7. And for the mesh anode and cathode, it's 365 microns. 365 exponent minus 6. It's actually in meters, it is 0.000365 in meters. And this is also mentioned in the guidebook how we calculated the values. Uh, Now the conductivity and the conducting zones, these are calculated in the Excel files. For the Excel files, you can see according to the properties given in both the references. They have given the composition reference, and from the compositions we can calculate the conductivities. So these conductivities are calculated in the accompanying Excel files. Right now we'll just follow directly give these values. So the conducting zones are the meshes are conducting interconnects. Only the channels, they are not non-conducting zones. And the contact surfaces, we'll come back at it. So AFL is a not functional layer 286. For CFL it is 5000. For ASL it is CCCL it is 10,000. Now these have very high conductivities. So the mesh anode is 2.433 exponent 6, and the same or for cathode is 1.54 exponent 7. The interconnects are referenced. The reference value is taken from the study of Esley. So the contact surfaces, now the contact surfaces are all the places where there's a change, a different entity, not within the cell but outside of the cell. So when the cell contacts with the mesh and the mesh contacts with the interconnects, so those are the contact surfaces. So we should have interconnect cathode with the mesh cathode. This is one of the contact surface, and CCCL with the mesh cathode. So this is a contact surface. So one is an interior and one is the wall. Wall is because there is a boundary between the fluid and solid zone, and the interior is because it is fluid and fluid. So the next should be the interior with ASL and mesh anode, not the channel. ASL and mesh anode, and the next will be again the wall for the interconnect anode and mesh anode. So these are the four surfaces that are mainly have the contact resistance, but for this study we will assume that there is no resistance or very negligible resistance. And now the voltage tap surface, we will directly select the voltage tap and the current tap. Voltage tap and the current tap. So this concludes the setting up the SOFC module, and now the next step is to go towards the material properties. Now the material properties also discussed extensively in the guidebook, so will just add all these materials. So we need to add the solid material, so here we'll make the all the materials that we need to define in our model. So we will make a new, and the name is AFL and not functional layer. Copy the anode default. Solid. So density is CP is 4, and the thermal conductivity is 6. Okay, we have created AFL layer, and now again a node default, we will just copy it to ASL. Again 7180, 74, 450, and 6. So we have created ASL. Now we will copy again cathode default or anode default. We just copy it. So we'll make CFL. Now for the CFL, it's the density is 50430, and cathode functional layer has a thermal conductivity of 2. Now CCCL 00 430, and again thermal conductivity of 2. We have got now the next two layers that we need are the meshes and then the interconnects. So we'll again copy any of it. So for mesh node, and now we copy it for mesh cathode. Or 8. This is 650.18. Now finally we need the interconnect. So just call it interconnect. Again, we don't need the aluminum for this, so we will delete it. And not default delete. It helps in deleting them because they help when we apply them to the zones. It creates less confusion. So now recheck all of these. So we have AFL, and recheck the properties over here that we have entered the correct properties. AFL, and then we have ASL, CFL, yes, CCCL, yes, and then we have the meshes, mesh anode, mesh cathode, and the interconnects. Yes. Now after defining the materials, now we need to apply them to the actual cell zones. So we have finished with the defining the materials. Now we need to apply those on the zones, and with the zones we need to select or specify the porosity of the material. Remind it then when we define the materials, we give a bulk and we give the skeletal density, not the density including the porosity. So we give the density of the material, of the solid material, assuming when we define the material over here in the materials, we assume that it has zero porosity, and then when defining the cell zone conditions, this is the time when we define the porosity. So we'll start defining it by starting with the AFL, and we'll go directly to the porous zones, and we can have the permeability or the inverse of permeability, which is absolute inverse of permeability. So we can calculate it. So the porous zone is So in the porous zones we'll define it. "15". This is the resistance. And now see that we need to define the porosity over here, 0.2, and this the material is AFL. Apply. And along with this we need to define the for the reaction purposes how much surface to volume ratio is there. So we define the active area, that is 1.35 exponent for this condition. Apply. So now this is now we have completed the term for AFL. Make sure that we have porous zone, source terms, and reactions. And close. Now ASL, in the same way we need to define the ASL also. And the porosity for the node support layer is the permeability is 5.4 exponent minus 15. So inverse of it is 1.85 exponent 14, and we'll copy it for all the others. And the porosity over here is 0.38, and we define it as ASL material. Apply. Now we need to define the reaction sites, so that is 1.05 exponential 3. Now we apply the CFL. It will be 1.111 exponent 15, and we'll copy it to all the others. Porosity over here is 0.27, and this is CFL material. Again, for the reaction site we need to give the reaction 2.4. So we have defined the CFL and now CCCL. Sorry, the porous zones, it's the same. And the porosity is also same, but the material is CCCL. And the reactions they will is 4.88 exponents. Six. Okay. Now for the channels we don't need to define anything for the channel or not. It's not a porous zone. It's no porous zone, but the reaction is included. There's no source term, but the reaction is included because there will be a change in the species, so the reaction should be there. Close. We don't need to define anything for the channels, but for mesh anode we need, because this is again a porous zone, so yes, we need. And it has got very less viscous resistance, so it's and porosity is 0.5. The material name is mesh anode. There's no reaction taking place over here, but since there will be change in the species concentration, so the reaction should be there, but the surface to volume ratio is 0, and it is also have a source term because there will be heat generated, so apply. Yes, and next is the mesh cathode. For the mesh cathode we have, it's also a porous zone with the same 1 exponent 12. And porosity is again 0.5, and now this is mesh cathode. I don't need to apply anything else. Close. And for the interconnects, you only need to define the material. Because it is a solid material, there is only source term available, but this is for the interconnects. Now with this, now we have defined all the materials and the boundary conditions we need to supply. Now the next task is the boundary conditions. We'll give the boundary conditions we have already discussed in the guidebook, so we'll just directly supply the values over here. So inlet is inlet and node is type as mass flow inlet. Seven. Thermal is at 750 degrees Celsius, so it is 1023 Kelvin, and the species are in mole fraction. H2 is 0.03 and H2 is 0.97. Cathode is also mass flow inlet. 6 species, and we can give 0.2333 as mass base, or directly we specify the mole fraction as 0.21. The rest will be nitrogen. Now from the inlet, we don't need to define anything in the internal. At the outlet, we have outlet anode. It should be pressure outlet at 0, and we will prevent the reverse flow condition. Likewise for the outlet of cathode, prevent the reverse flow. Now we have defined all the things necessary for the simulation, but to get a proper simulation we need to define the report definitions. Hey, we already previously set all the report definitions, but we still need to set the report definition so we can directly import it using. We've already discussed in details how to set the report definitions in the previous chapters. So the same way, these are the same expressions and the report definitions, but only the areas selections are changed. So right now we'll just import the report definitions, import from file, and we can go here from TSV. So I already saved the report definitions previously, so I'll just import the report definitions. So we import the report definitions. You can see, okay, now these are invalid, and we import the named expressions. So now we have the named expressions for percentage valuation. And now the next thing is that we need to so the next thing is that we need to define, sorry, yes, sorry. So then the next thing that we need to define is the partitions. So we'll go to the solutions and parallel setting and load partition. So we would like to make it auto partition, but number of partitions, and we can have different options, but we need to study. I think I need to study more about these. So we'll just for now we'll just select the metas method and partition it. And next, cutoff ratio, Laplace smoothing, and smooth, maybe let's like 10 iterations. Okay, and use stored partitions. Okay, so this is still a little bit bad. so the partition is not really that good. So we can see the partitions if we go to the domain and display, and here we can see the partitions display. So if we can have the transparency, see the partition is really not that good, but we have, like, it should ideally should have been like a cross. So let's turn off the grid. You see, this is the type of partition that we are having in our cell. Not a perfect partition, but still it's good. Maybe we can partition more. And if we go to the parallel, then obviously we can't cutoff ratio, aspect ratio. Sorry, 2. And now display again. Not much has changed. Okay, so but we have given it smoothing. Okay, so just use stored partitions, and we'll move further. Close. Okay, so now the next part we have given the report definitions and the named expressions. Now we need to set the monitors. For the monitors, we will set again, as we did previously, we will set all the monitors for and the report plots also. So we'll set the monitors, report files and report plots. For the report plot, we will first set edit, no, report plot new, and we want to look into the temperatures and cell current, cell voltages, and the species utilization of H2 and O2. So we'll first go into the temperature. Minimum and maximum temperatures. So we'll select the temperatures, maximum and minimum temperatures, and this should be min and max temperatures. Okay, so we got the first report plot and new. The next we want is the utilization to utilization. So we'll have fuel utilization and O2 utilization. H2 O2 utilization. Next we have the minimum mole fractions. So we have to give H2 O2 minimum mole fractions, and we'll first should include for the fuel H2 minimum mole fraction at the electrolyte, and we'll add O2 minimum mole fraction at the electrolyte. Fractions. So the next is cell voltage and cell current. So we'll add new as cell currents. This have cell current and cell voltage. We have the voltage and we'll select the cell voltage. Now we have made all the report plots and now we need to define the report file. For the report file, we'll add a new report file, and the things that are very essential for the report file are especially the cell current, cell voltages. So we'll have all of these cell currents and cell voltage and then along with it we need to have the fuel utilization, oxygen utilization. It is also important that we have the temperatures, and then just in case for the minimum mole fractions also available at the electrolyte. And when we are doing the parametric analysis, it is important that we have the information about the inlets and outlets, the mass flow at the inlet and the mass flow at the outlet. So we should add the mass flows also, mass flow anode and mass flow cathode. Okay, now with this we can finalize our report file. So we can get the data after every 10 iterations, and that's good. So now we have set all the things that are necessary for to start the simulation. So for the initial method, we will set the solution to for standard initialization, but before initialization we should set the temperature up to, because we are operating at 800 degrees Celsius, so we should set it around 800 degrees Celsius. That is actually 1073 Kelvin, and it is a full 3D model, so this type of initialization will work, but we need to have some more we need to increase the under relaxation factor for the momentum also. So if you could, so if you go to the options, sorry, advanced, this is not this one, controls. Yes, here for the first couple of iterations, for at least we already reduced the current value also, and for the momentum we need to decrease the momentum under relaxation to 0.5. So with this setting we should initialize it. Now when the initialization is done, so yes, everything is correct. So and here we have already give the temperature also, we have initialized it, so we can start the initial run for just 50 iterations, and then we will again modify it for further. So let's give 50 iterations and calculate it. As you can see, even though we gave a very small value for the current under relaxation, the temperature is being limited to a really high value. So if you go to the minimum maximum temperature, it's going really high. But it will start decreasing afterwards. We already gave the initial temperature near, otherwise there would have been more fluctuations. So it will stabilize after a few iterations. So, actually the voltage should increase because I've got a very small value for the current, so the voltage should go as near as OCP. That should be around 1.1 or to from between 1.1 to 1.2 volts. So let's let it complete the 50 iterations, and then because the solution will have converged quite some bit, it will have good values in all the nodes. So then we can decrease and increase the relaxation factor for momentum and for the current also. As you can see, it's a full 3D model, so there are many problems that can occur. So it didn't even completed the 50 iterations. So let's see, maybe we can have the utilization actually went way down. So this is not an a proper, this is a imaginary case, so it went really low, which is an imaginary value, so it was not able to solve for it. So maybe we can, for to solve this type of issue, we should for the time being initialize it again, and then yes, discard the data, and domain display, we don't need to see the partitions, sorry, display 0. Okay, and now but everything else is okay, but we need to remove it. So from the report files, in the report file we will remove the oxygen utilization for now, and then we will add it again, and from the auto utilization also we will remove it for now. Okay, and then calculate it again. As you can see, it failed again, so there was not a problem for the expressions, so we just included all the expressions. So there's probably some problem with the species, so we need to have an under relaxation factor, or we need to go to the advanced controls. And now the electric potential, we BCG tab, and energy we go for BCG tab. Okay, and for the energy momentum, for the options, sorry, as for the controls are, so we will decrease the momentum from 0.7 to 0.3, and reinitialize it again, And now if we will include again back everything in the report file also, and this report plots also, and try to solve it again. Now we'll include the O2 utilization. Earlier we did removed it, I think we did. Utilization, and from here also just do an auto utilization, and we'll include the auto utilization. And in the file report we have fuel utilization, auto utilization. Okay, and then let's calculate again. Now we decrease the momentum to 0.3 and started the advanced. From the advanced controls we used BCG stabilization also. So now as a result you see it is getting much better convergence. It is showing very good convergence for temperatures, H2 and O2 utilization also, and the minimum mole fractions. So everything is going well, and the currents are also converging properly, and especially the voltage now it has certainly raised, and this will minimize the fluctuations also. Now the calculation actually completed properly with proper convergence, so we can see that the solution converged properly, and the value over here is in exponent -4, so it's really good convergence. Maximum temperatures they went up to 1023, which was the near the, because it is not operating, so it should be like this. And fuel utilization should be minimal. Current is almost 0.01, which is the desired current that we gave, and this is the almost near the OCV 1.1076. So but we should complete the 100 iterations, but however for this now we will increase the momentum to 0.7, and going on to into the models, and we can increase the under relaxation factor to 0.3, and we will again give the next number of iterations, the next 15 number of iterations, so we continue. So with this we complete the simulation for the 100 iterations. Now the solution is completely converged, and okay, take some time to load everything. Okay, now see the scaled residuals. After we increase the momentum, still it converged properly up to exponent -5, and we have got the temperatures are stabilized. Voltage, we have got the OCV voltage now. This is about 1.1076, so this is everything is really converged properly, and now we can the minimum mole fractions also, so 0.2098. And so with this we can conclude our simulation, and we will continue it with the parametric analysis. So now we should save it, so let's save project and write the results also. And so here if you see that if we go to the workbench module, now we have got to take out the solution also, so we have got solutions available, the project is written, and we should write the results. You can save the results also, but okay, that's in the project they are saved. Okay, that will be all. Thank you and bye.